right, so remember, all I'm doing here is just putting in different temperatures for these different nebula. All right, so for M8 it's 7,500. For M16 it was 8,000. All right, so this is just the temperature. So you're just putting in, instead of, you're just putting in the temperature right here, right, and that's high. And then for M17 it was 8,700. All right, and so the next one, the last one. All right, so for the last one, M20, which has a temperature of 8,200 Kelvin, you just take the square root of that and multiply by 0.157, and you get 14.2. So 14.2 kilometers per second. So remember, that's what the average molecular speed would be, for these things, given their temperature. All right. So the second part of this is a little bit more complicated. What they're doing is, so it says to, let's see, you want to estimate the escape speed near the edge of the 4 emission nebulas. Okay, so the thing about it is they give you the diameter and the mass of these things, and the only way that you can do that, of course, is to know. Let's write down the equation. Okay, so for the escape velocity, this is true for anything in the universe, right? The escape velocity is equal to the square root of 2 times this constant, which is the universal gravitational constant, times the mass of the object, divided by the distance from the center of the object, which we'll call r. All right, so r is the rate. Like if it's spherical, these aren't necessarily spherical, but if it's the spherical, that would be like the radius of the sun. How if you put the mass of the sun and the radius of the sun, you could work this out. All right, so we have to just do each of these, one at a time, right? Using this formula. So for the first formula, M8, right? Remember M8. They give us the mass is 2,600 times the mass of the sun, and they also give us the radius. All right, so this is the thing that we're gonna have to figure this out. So the mass is 2,600, and of course times the mass of the sun, right? Which of course the mass of the sun is 2 times 10 to the 30th, right, in kilograms. All right, so you can figure out what that is, and let's see. I think it comes out to be 5.2. That's supposed to be a 5 times 10 to the 33rd. Right. Remember, this is a cloud of material, or gas, mostly hydrogen. All right. So that's the mass of this, and the radius of it. Well, they give us the diameter as 14 parsecs. So the radius is going to be 14 parsecs divided by 2, which of course is trivial. But then we got to convert the parsecs to meters, right? So in 1 parsec. So we're going to keep doing this for all 4 of them, right? So this is just the one for M8. So we got to do it for M16, M17, and M20. All right, it takes a while to do each one of these. So anyhow, in 1 parsec there are 3. What is it? It's 3.1. This is a good approximation. 3.1 times 10 to the 16th meters. All right, so you just multiply 7 times, the parsecs cancel. 7 times 3.1 times 10 to the 16th gives us, what, 2.17. So 2.17 times 10 to the 17th meters. 17th meters. Okay, so these two numbers you put in for M and for R. All right, so G is just a constant of the universe. It's always the same. And of course, 2 is always the same. All right, so we're going to put those in and calculate the escape velocity of gas just at the edge, 7 parsecs from the center of this this cloud. All right, so just at the edge of the cloud. So this is the formula. So this is, and I haven't put the radius in, divided by the radius, which turns out to be 2.17 times 10 to the 17th. All right, so those numbers are correct to calculate the escape speed for gas just at the edge of this nebula M8. Just as a reminder, remember when we did the molecular velocity, just using the temperature, the molecular velocity was that was an average for this particular nebula was 13.6, right? 13.6 kilometers per second. Now, by the way, the numbers here come out in meters per second, but we'll change them to kilometers per second. So I think it comes out, let's see, when I did this, I think it comes out to be 1,800 or so meters per second, which of course, if to turn it into kilometers per second, you just move the decimal place 3 places to the left, and so this becomes 1.8 kilometers per second. All right, so again, you're going to use this same formula exactly, but you have to get the mass of each individual nebula and the radius of each individual nebula, which is all listed in that table 18.1. All right, so I don't know if you really want me to go through each one of these. I guess I can. Hold on, let me. All right, for the next one, which is M16. All right, I'll go through this. M16. They give us the it's 600 times the mass of the sun, which is 600 times 2 times 10 to the 30th kilograms, and so that's the mass. And the radius is what is it? 8. Is that right? 8 parsecs. So 8. And then that's the diameter, so we got to divide by 2, and then we do that conversion by multiplying by 3.1 times 10 to the 16th to convert it into meters. All right, and so that turns out to be, what does it turn? All right, just left that in my calculator. Anyhow, so remember the escape's velocity is the square root of 2 times big G, which is 6. Well, I'll just do it like this: big G times the mass, right? And we're going to use this mass and divided by the radius, where you're going to use this radius, all right, with whatever this comes out to be. Anyhow, when I did this, it turns out to be, remember, it comes out in meters per second. So to compare it to the other one, convert it to kilometers per second, and so it comes out, which one was this? M16, 1.14. So this comes out to be 1.14 kilometers per second. So, it was, the answer actually came out to be 1,140 something meters per second. All right, so that's, just to remind you, the that's much smaller than for the molecular gas velocity, right? Just as a reminder, the molecular gas was moving at 14 kilometers per second, right? We'd already calculated that due to the temperature. So this is much larger, right? That's much larger than that. So in other words, the whole point of this exercise is in each of these nebula, the escape velocity of the gas is not great enough to hold the gas in place, right? That, in other words, this thing is still forming, right? It's still undergoing formation. Right, anyhow, let's keep going, and not only that, there's other things that that prevent the gravitational collapse, the rotation, and also magnetic fields. All right, so all right, let's go on to the next one. I'm just going to give you the numbers for M17, right? So here's M17. Just as a reminder, the escape velocity, we got to calculate that, but they give us the numbers for that. Let's see, this is M17. When I did it, I got the escape velocity as 1.1 kilometers per second. And just as a reminder, the molecular speed was much greater, right? So in other words, it was 14 kilometers per second, right? Because of the heat. And so this is much greater, right? Sometimes people write it like that. That's much greater than the escape speed. So the gas would easily escape, right? Even at the edge at where the escape speed is 1.1. It's just not enough. There's not enough mass there to hold it yet, right? So there's still material that this thing has to build. All right, and the last one I think was M20, and when I calculated the escape speed for that one, here's what I got. Where is it? M20. Here it is. That one's really small. So that one has an escape speed of 0.58 kilometers per second. Just to remind you, for that particular one, the molecular speed was, again, much greater. It was 14.2, right, kilometers per second. So again, it could easily escape. The gas could easily escape. All right, well, let's do the last one. It doesn't take all that long. All right, finally, number 8. Okay, so number 8 says, to carry enough energy to ionize hydrogen atom, a photon must have a wavelength less than 9.12 times 10 to the minus 8th. Use Wien's law to calculate the temperature a star must have for the peak wavelength of the blackbody curve to equal this value. All right, so this is what we do. There's Wien's law. This constant 2.9 times 10 to the minus 3rd, because we were in meters, times Kelvin, divided by that wavelength that they gave us, which was 9.12 times 10 to the minus 8th. That gives you a temperature of the star of 31,798 Kelvin. All right, just to let you know, the only stars that are that hot are O stars. All right, so the spectral classification are O-type stars. So and in fact, that's why you find stars. That's why you find, ionized, hydrogen, and you even find, for example, other ionized things, but certainly ionized hydrogen in these O-type stars. All right, that's the last one.